See, we've got an equation that tells you how to do that. Because if you keep your soil moist and cool, okay, you can reduce that re-radiation 80-90%. Okay, so you can turn down the greenhouse effect. You can do it in days. It's as simple as not mowing your lawn. But sponge. Okay, that's the key thing, the sponge.
Welcome to everybody, because as you all know, these are trying times, but there are all these alternatives that we can do in our own homes, in our communities, in supporting people around the country and around the world. So Walter Jehne, who I asked him what I should tell you about him, and he said, nothing. So I'll tell you next to nothing. He is a soil scientist, microbiologist, and a climate scientist, and he's got a vast knowledge of the planetary situation and has been traveling around the world talking to people high and low. That's not a good scale. People with big mouths and people who listen. It's more like it. To present them with the solutions that they really don't know about. And these solutions are inexpensive. Anybody can do them. It's just a question of cultural and mind shift. So, without further ado, Walter Jehne.
Right. Look, thank you very much. Can you hear me okay with this mic? Right, wonderful. Look, thank you very much for coming this evening, and let's have a big discussion about this, because basically, as Adam said, there's a major crisis that we're facing, but there's also really beautiful, natural, safe solutions. So it's in a sense exploring that reality that we're facing after 40 years of basic inaction, but then let's look at that potential for what we can do to safely, naturally cool the planet in time, but also rebuild biosystem, revitalize communities, rebuild a healthy future for everybody. So there's a really positive upside. Bit of background. I mean, I just wanted to say, look, let's talk for about 45 minutes, but then really I'd like to have a Q&A. I want to spend most of the time listening to what you're saying, the questions, and then sort of coming back and saying, look, here's the answers, and perhaps outlining details and stuff like that. So I'll be going over fairly quickly initially as the key basis of what we're talking about, but then really want to explore your specific questions and then explain things in detail. At the end, I think it'd be really nice to have a sort of a bit of a panel discussion, because I don't come from Boston. I come from down under. You have to drill quite a bit down, 12,000 kilometers. You get to Australia, where I come from. And so, basically then let's have that, panel discussion and really get through all those questions. But in terms of just background, look, I'm a soil microbiologist from down under, under. And basically, I spent my initial, 15 or so years as a research scientist with our government, but then moved into actually innovation, the strategic sort of innovation, commercialization issues. But about 15 years ago, I retired and went back to working with farmers, some really innovative leading farmers, initially in Australia, doing absolutely stunning things, regenerating the earth, regenerating biosystems, regenerating the earth's soil carbon sponge. Okay, so that's one big word, very important. All our discussions really range and focus on, okay, how do we regenerate the Earth's soil carbon sponge? Because that's the solution, the take-home message. Okay, and so basically initially working with these innovators in Australia, I also worked very much at a fairly senior policy level in government, sort of bringing this whole debate into policy, strategic policy directions. But basically that's excellent, but in a sense politics talks the talk. And it's really the people, you on the ground, who are actually implementing the change. So the change has to come from the grassroots, community groups implementing change, and then very quickly the logic, the compelling evidence of that change becomes apparent, and that in a sense what drives and catalyzes that bigger policy agenda. So it is very much about empowering the grassroots, and this comes back to Paul Hawkins and the whole idea of blessed unrest, where basically it's literally millions of NGOs and groups around the world who are driving this change. And you're part of it because just by participating in these discussions, this is the frontier. Okay, so that's basically the picture. And now, more recently, actually, we've gone, in a sense, global with a new NGO called Regenerate Earth. And that NGO is really now networking with a whole lot of people, different meetings in basically all continents of the planet, driving, again, this change, but again, all focusing on the sponge, right? So never lose the sponge. Okay, to start the sort of story in a way, I suppose it comes back to you or us collectively. There are now 7.5 billion people on this planet. Okay, we're going to expect 10 billion people by mid-centuries. And in a sense, that's unavoidable. And 8 billion of those will be living in cities. And so as we already know that the water, the food, the habitat, the safe climate, the social stability for those 10 billion people is critical. Okay, and in a sense, I don't know if any of you have got sort of these strategic connections, but really globally, that's been the key issue of concern. Okay, how do we meet the needs of those 10 billion people, whether it's the UN Sustainability Development Goals, or actually if it's strategic interest, how do we actually keep social stability? And the risk of 7 missed meals between social stability and chaos. Okay, and that's the Arab Spring or Syria. It's very real, and that's in a sense what, in a sense, society has to avoid. And the beautiful news is we can avoid it. But then we have to sort of say, well, look, what are the realities that we're facing? And Adam's already raised them. And of course, we've had, 50 years since limits of growth, and that whole message that, hey, resources don't basically last forever. We can't sustain a linear, extractive, exploitive economy. But now, 50 years later, something more serious has happened, because now we're getting nature coming back with feedbacks. Okay, you stretch a system too far, and nature starts signaling very, very, initially subtly, but very, very firmly, that, hey, things aren't as they should be. And we're getting those feedbacks already, and these are the dangerous hydrological climate extremes. Okay, and we see them all around us. They're intensifying now, whether it's hurricanes, floods, erosion, damage, sea level rise, inundation. But also, as we have a flood, that's lost water. And of course, we're getting the exact parallel. With every flood, it's followed by a drought, because that water is no longer in the landscape. Okay? And so basically the flood creates the drought, creates aridification, desertification, and of course from that we face the next really serious prospect of wildfires. And of course we're getting that message loud and clear, whether it's paradise is burning in California, Alaska, northern Canada, Siberia, Brazil, Africa, Australia. We've had fires for a long, long time, so we know what the basic destructive fires are. But mostly it's the actual collapse of biosystems because of fires, the desertification of landscapes because of fires. You see, and so we can come that. And basically there's some very beautiful, simple little stories that we can tell about this. And again, this is what's called a hygrograph. And in a sense, it's telling us exactly what's happening and what we need to do, because basically this measures flow in a sense, runoff flow, and this is, of course, time. And if we get a rain event, just say 2 inches of rain in a landscape, if we have a concreted catchment, a degraded concreted catchment, we already know what will happen. We get this massive flood peak, and then it basically disappears. And of course, this flood peak is really basically all about risk, damage, and of course, really causing a lot of destruction. Of course, this is major costs to the community, to the individual, or to insurance industries, for example. But what people, in a sense, don't see, that this is also really creating, in a sense, the drought that follows. Okay, because that water that basically flooded off is now no longer there. So you're getting not just drought, but loss of productivity, and the whole biosystem, in a sense, comes to collapse. And in a sense, lapse. And that's, in a sense, the story we're facing. And why? Because basically we have degraded or concreted that catchment, and often we've got soils now around the world with less than 0.5% carbon. You know, it's about 0.8% organic matter in the soil. That soil can't hold water. So that's 0.8% organic matter. Okay, percentage. But of course, if we look at what happened in nature, we've got a completely different story, because while the soils, in a sense, were in their natural, healthier state with a sponge, and again, we bring this up, and even just 3% organic matter in the soil, then we can create a completely different hydrological profile, because the same storm event will now create, in a sense, an infiltration water retention event. Okay, so if we say here's 0.3, yeah, you'll get some runoff. Okay, but most of that water has gone into the sponge and then into the in-soil reservoirs. And the powerful thing about these in-soil reservoirs, it avoids all these problems. So we've got massive savings, whether it's in risk and damage and cost. Okay, massive savings. You basically, you all live in cities, you all live in counties, 90% civil engineering, you don't need the stormwater, concrete, the drains, all that capital expenditure. So in a sense, you're having these savings. But you've got another thing now what happens, because now you have longevity of green. So I'm a bit scrappy here writing, but longevity of green growth, which means that in a sense our forests, our pastures, our fields are able to extend the length of their growing season because there's soil water. Whereas here, of course, it very rapidly went back to desert. And we can get basically, rather than having 3 or 10 days of water supply under this system in that soil, we can give 100, 150 days water supply. And so now we're talking about 1,000% or more of green productivity response. And that's mind-blowing because, in a sense, all our green revolution science, I was part of that, never got beyond 30, 50% growth response. But here we're talking about 1,000 plus just through nature, longevity of green through the sponge. So when we talk about these dangerous hydrological extremes, we've got to really focus on the key thing of, here's buffering and resilience. Okay, and that really becomes the key part of our challenge. It's as simple as this little graph. Obviously, this is a simple area. There's one storm on a landscape, and here are 2 contrasting A and B, basically totally different response curves. And so the question really is to anyone who'd rather live in A or who'd rather live in B. You see, and who's going to survive under A and who's going to survive under B. And it's that fundamental, you see. And of course, it's all about, you can all say it aloud, rebuilding the Earth's soil carbon sponge. Okay? And in a sense, that then steps it back. I'm pretty old, but microbiology is even older. And when you think, how did nature actually create the biosystems that we fundamentally depend on? When you think of it, all she had was sunshine, CO2, water, and stardust, which then collapsed to make 9 planets. But the bureaucrats have dropped Pluto off the list, but we don't worry about that. Okay, stardust, nutrients, elements, the periodic table. And then, of course, basically nature sort of 3.8 billion years ago took those elements and evolved the first living microbial cell, a bacteria around, hydrothermal vents in the ocean, from the best of our understanding. About 3.5 billion years ago, nature took the next step, invented photosynthesis, the capacity to capture solar energy by blue-green algae to convert that solar energy, CO2 and water, into sugars. And of course, since then, that had that energy source to drive life through photosynthesis. But the real step for terrestrial life, for life on land, was really 420 million years ago, when all we had is ocean and bare, hard, arid rock. No life on land. But the oceans were limited by nutrients leaching from the rock because we'd had the Cambrian explosion, so there was lots of animal life in the oceans. So there was a major competitive advantage of basically getting minerals from the land to, in a sense, drive bioproductivity in the oceans. And of course, to do that, fungi, tubes, mycelial tubes, like membrane tubes, grew from the estuarine edges onto the rock to solubilize nutrients, because that's what the fungi are excellent at doing. They've got all the enzymes for doing that. But fungi are like us, they basically are proto-animals, and they can't photosynthesize. So they had to basically make a partnership with blue-green algae and, of course, form lichens. And everywhere around Boston and New England, every rock, every forest tree, every bit of concrete, every bit of asphalt, you'll see these lichens. And they're solubilizing all that rock, all that hard-edged stuff to get nutrients. But as they grow, they also leave behind organic detritus, which of course mixes with the mineral detritus and forms the first soils, the first sponge. Okay, so there's, in a sense, the pedogenesis process, the soil-forming processes, basically microorganisms, fungi, and algae in lichens forming organic detritus to create the sponge. Yeah. And in a sense, that sponge very, very rapidly gave rise to that soil being able to hold water, infiltrate, retain water. And as you can see on most rocks out here in New England, very rapidly go from, supporting lichens to mosses to liverworts to ferns to cycads, or you don't have cycads, we have cycads. But the point is, then gymnosperms, angiosperms, and fairly recently, grasses. So that whole rapid succession and evolution of life on land was all driven by pedogenesis, the Earth's soil carbon sponge. Okay, and very rapidly the whole Earth's surface, the 14 billion hectares of land on this planet, was then covered by vegetation through these soil-forming processes. So soils are fundamental, but more importantly, the sponge is fundamental. So you create the sponge, and we can create life. We can regenerate the hydrology of that landscape, and we'll come to that later. We can also restore the natural, safe cooling of the landscape, because it's basically, as the biosystems evolved, so did obviously the sponge, so did vegetation, and so did a whole sequence of natural cooling processes. Okay, so really what we've gone through is, in a sense, yes, what the sponge is about, how nature, in a sense, evolved the sponge. And I suppose we now have to say, well, look, what have we done to this? You know, where are we now? And what's the sort of consequence of what we've done? Because then that can actually tell us also, you know, like in a sense, what we have to do to fix things. And I'd been talking earlier, so we already drew this thing, and the message came very clearly, you know, 1958, Charles Keeling, right? And in a sense, we had speculated on this, or not speculated, we'd done calculations, Cervantes Arrhenius, a Swede, back in 1896, but basically he, for the first time, made that sort of hard evidence to say, look, here's CO2, here's time, and of course here's CO2 going up. Okay, so Charles Keeling 50 years ago gave us that first hard evidence. Here is CO2 rising, initially from the 300 parts per million, or 280 parts per million previously. It had been going up from about 1750, you know, the last 250 years. And of course we now know it's, 410 parts per million, might be one or two higher. Probably people got an more accurate figure. But the point is that we've raised the CO2 up. And again, that's what we've focused on. Yes, and of course CO2 is a greenhouse gas. Definitely CO2 basically is about 11% of the greenhouse gas effect, and certainly it drives about 4% of the global heat dynamics. But we'll come on to that later as well. But what Charles Keeling really sort of told us, something much, much more important, because you've all seen the Charles Keeling graph, you know, the steps. I mean, I've accentuated them on this for illustration purposes. But every winter in the Northern Hemisphere particularly, we've got basically emissions, right? So we've got about 130 billion tons of carbon per annum that is being emitted globally, in a sense, every Northern Hemisphere winter. I mean, the opposite happens in the Southern Hemisphere, but it's not as marked. So we've got this massive emission of CO2. And then every year in spring and summer, when, in a sense, vegetation comes out, we have about 120 billion tons of carbon being drawn down by the residual biosystems that still exist on this planet. We'll come back into that in a minute again. And so that's giving us about a 10 billion tons carbon per annum deficit. And it's because that deficit is happening every year, that's in a sense why CO2 is going up. Okay, and so we've basically spent, 40, 50 years focused on, yes, we've got an abnormal CO2 rise. Yes, CO2 is a greenhouse gas. No argument about it. The science is absolutely hard, impeccable. And basically everyone's focused, okay, we've got to sort of, in a sense, reverse the emissions of CO2. We've also basically had the picture that, we've got about 10 billion tons per annum deficit, and we've got about 8 billion tons of emission from fossil fuels. So people have really taken the analogy straight. Look, okay, if we reduce or eliminate fossil fuels, we can actually do a lot of this, a lot of this gap we can address. And in a sense, that's where we've been stuck in climate change, right? We've been basically focused, okay, we've got a deficit, we've got this fossil fuel use. Hey, how do we stop fossil fuel? But we have a problem, you see, because as I said in the beginning, there are 7.5 billion of us. 10 billion expected in 30 years' time. And of course, we all like to eat. And at the moment, we're using 10 units of fossil fuel energy to produce every unit of food energy we eat from the industrial food system. You see, and so the question is, have we got 6 billion volunteers who want to drop off the perch amongst Homo hubris? No. You see, and that's the trouble. See, how do we actually now, this issue of social stability and strategically planning, right? We've grown the population. It was 3 billion when I started as a researcher. It's now 7.5. But yeah, we've got to look after 7.5 to 10 billion people. So how do we do that? Because if we kill all fossil fuel use, then we can't sustain this population. There's no one saying that we mustn't reduce the fossil fuel potential, and we've done a lot of work, whether it's solar energy or renewable energy. But yeah, 1 to 2 billion tons of carbon would be a champion effort to reduce that. But of course, it's nowhere near enough to drop that 10. So what we've simply done, and it's very simple, logical. See, basically science has said, look, see this 250 billion ton dynamic that nature has. They sort of said, look, that's nature's problem, right? And they've just focused on this. But if we look at this thing, the question is, can we intervene? Can we naturally regenerate? Can we actually intervene in this process, these 250 billion tons, not just to get 10 billion tons, but can we actually get 20 billion tons of carbon, in a sense, emission reduction and drawdown, to take CO2 back to negative or basically former stable levels. Okay. Let's do it, Jim. Yeah, absolutely. Good. Now that comes the next point, you see, because then the answer is, how do we do it? And we had some of those discussions earlier because, see, basically every year we've got 350 million tons of forest with between 50 and 200 tons of carbon emitted every time they burn. So that's what we're burning globally. It's about 10% of the global forest, residual forest area. And we're burning 10% of it, whether it's in Paradise, Alaska, Canada, Siberia, Africa, the Amazon. Okay? So the amount of emissions, depending on how severe the fires and what forests are, immense. They actually can exceed the fossil fuel emissions. On top of that, every year, 2 billion tons of grassland burns with about 3 tons of carbon per hectare emitted. Okay, so there's another 6 billion tons of carbon being emitted just through grassland and crop waste burning. Okay, and so what we're doing, Jim, is just sort of saying, look, hey, there's all areas where we can intervene in this game to get to that 20 billion tons. So the Regenerate Earth story, it's all positive. If we just say, limit wildfires, in these areas, yes, we can get there. And of course, you ask, how does nature limit wildfires? Guess what? It uses fungi. It rots down that forest fuel, that grass fuel, rots it down into sponge, stable soil carbon in your soil, which holds more water, which stops the wildfires. So you both remove the fuel, but also you create a more mesic, a more better watered, higher soil moisture level with less fire risk. Now, no one's going to say we're going to stop all fires. It's wrong. But how much can we actually help there? And of course, if we can put that carbon that we're losing in fire into the actual soil to rehydrate, and we're back into this longevity green story, it's green, so we can have a green thing. See, then the answer is, we've got forests. We've got 3.5 billion hectares of forest. This is the residual forest we have. We used to have 8 billion hectares 10,000 years ago. We've cleared 6.3 billion of it, but about 1.8 billion is regenerated, largely here in New England, okay, and other parts of the world, Europe. But basically, there's 3.5 billion hectares, but can we actually add another 20% carbon drawdown in that forest if we actually regenerate the sponge? And the answer is, of course, the forest tells us, yes, we can. Easy. Easy. Can we have, in a sense, running out of colours, but can we have grazing management, right? Can we have grazing management, wise, holistic grazing, ecological grazing, and basically not overstock and overgraze and desertify land, but use those grazing animals as tools to actually optimally manage that rangeland. And of course, we've got 5 billion hectares of grasslands and rangelands that are being grazed by herbivores. And the optimum management of those ecosystems, again, can put an extra 1 to 2 tons of carbon per hectare into that land. Okay, 1 to 2 tons over 5 billion hectares. Again, there's 5 billion tons adding to our 20 billion tons. Okay, wetlands, right? We've got basically half of eastern North America, well, not half, but vast areas were wetlands, but we can restore vast areas of these wetlands naturally. Used to have 200 million beavers in North America, building wetlands, building sponges, because that's all a wetland ends up, wonderful sponges. We drained those wetlands because that was where the beautiful organic soils were, that we could go on and straight away grow potatoes and corn and all the crops that colonization, in a sense, needed to survive. You know, drained beaver meadows. Okay, but can we bring that back? And then how much extra carbon could we store? How much extra water can we store? As I said, we've got 14 billion hectares of land on this planet. They're not making any more of it. Some is going to go under with sea level rise if we don't get our act together. Okay? But basically, we've created 5 billion hectares of man-made desert and wasteland. And again, what can we do? Arid zone, regeneration, rehydration, revegetation. You in America get 40% of your food from the Central Valley in California. Okay, it's within 10 years of desertifying, kaput. No more snow melt, you've drained the aquifers, you've stopped the humid, moist air inflows, the biotic pumps from the Pacific Oceans. It's cactus. 10 years, Central Valley, 40% of US food. Unless we pull our finger out. The answer is yes. How do we rehydrate, regenerate, and build the sponge, rebuild this ecology on the Central Valley, California? Didi and team have been there. Asking the question, can we rehydrate California? Workshopping at the local level and looking at, yes, we can. But it all involves a change. Okay, and so basically, I mean, there's more detail here. You know, we can keep on going. You know, cement manufacturer and savings there. I mean, just here, look, we're using massive amount of cement in urban infrastructure, pavements, roads, sewerage, drainage, dams, massively. Okay, all that cement is calcium carbonate that they have to burn, heat, to emit CO2 from it to form calcium oxide. And all those emissions, you know, 2 to 3 billion tons of emissions every year from making cement. And how much can we actually save just by having a sponge? Okay, so that story is basically, we've got dangerous hydrological extremes. They're going to really impact severely in the next 10 years, you know, like whether it's Irene or Sandy or Katrina or droughts or fires, right? Really severely. We're in Australia, we're under systemic aridification. Okay, we're getting 30% less rainfall and basically 50% less runoff. You know, we've had peasants walking off the Fertile Crescent in Syria for the last 20 years because they basically degraded and desertified their soils. They've had to walk into Damascus, walk into Aleppo, and we know the sad civil war and stuff that follows. Okay, and that's Syria. I mean, there's other factors there, of course, but the same issue is now happening. We were just actually at a conference, and there's people from southern France and Spain, and it's real. It's happening. It's happening in California. So we've got to really think, we've got 10 years, so how do we do it? And all we're saying is, yes, Charles Keeling, but nature really has told us we have 250 billion tons of carbon. And we've got to start changing our mindset. This carbon isn't a problem. the carbon is a symptom of our land management missed opportunities. More importantly, the carbon is a resource, the building block to rebuild the sponge. Because all a sponge is basically mineral detritus glued together with bits of carbon, 3% carbon, just gluing that together. And then a healthy soil is, in a sense, a matrix of voids and spaces and air, okay, in a soil. And it's that air, those voids, those cathedral of voids and spaces in that soil, which is where the water infiltration, where the rootability of that soil to depth, where the nutrient availability and biofertility is enhanced because the vast surface areas that are exposed, okay? And basically, it's the sponge, just simply putting that 3% of carbon into that soil through biological processes that, in a sense, can get that 20 billion tons drawn down, rebuild healthy, resilient systems. Okay, so that sounds like a good story, doesn't it? I mean, that's really quite exciting, but I hate to disappoint everybody. It won't help us at all. It's far too little. Because as we already know, and science has no questions about this, you see, every bit of carbon that we draw down will be re-equilibrated by the world's oceans. Okay, the oceans contain 38,000 billion tons of carbon dissolved CO2. And as they warm and as they acidify, they're, in a sense, re-equilibrating that carbon back into the air. And of course, every bit that we draw down, they will simply rebuffer, re-equilibrate and say, thank you very much. The oceans at the moment are absorbing 93% of the extra heat we're retaining on this planet. Okay, so it's a very, very slow, heating, degradation and collapse sort of situation. So even if we pull down carbon valiantly at 20 billion tons a year, by itself, it's not going to save us. It'll take us literally centuries to have that effect. So we've got to do something smarter, don't we? Much smarter. But in a sense, nature has given us a sponge, so in a sense, we do already have the solution. But to do that, we have to actually do what Einstein told us. We have to look at the problem in the sense you can't solve any problem with the same thinking that created it. Okay, we've got to get outside our existing paradigm, just as we did here. It's not CO2 deficit and fossil fuels. We've increased the whole paradigm to say, let's play in this bigger sandpit of nature. And then we can solve it. But the same comes with cooling, right? Because now we've got to find a way, how do we safely, naturally cool the climate to offset, in a sense, the warming, but to offset these dangerous hydrological climate extremes that are impacting now. So in a sense, the whole paradigm has changed. It's really quite interesting because we've been talking about this cooling, hydrological cooling, for about 10 years. And invariably, like at first it was just, hey, what are those wackos on about, right? But then progressively, there's a bit of rubbishing. The academic says, where's all the published papers that haven't been funded, but they still expect them. And then basically now it's coming, hey, can you come to a UN conference and talk to this, or can we have a think tank exploring this possibility? So we're now at that tipping point of change, because the realization globally in the climate debate at that strategic senior levels, yes, it's all about dangerous hydrological extremes, and it's no longer good enough to just talk carbon. We've got to go into a new paradigm. How do we safely, naturally cool the planet? So again, we simply ask the question, how do we do that? How do we cool the planet? And again, we can just sort of go through, well, what is the actual reality that we're facing as far as global warming? And of course, we've got this guy, or her, she's a sun. Okay, there's a sun. Okay, and we'll make that blue because we're talking about the blue planet. Okay, and there's, in a sense, a planet. And of course, every day, continually, basically the sun is giving us 342 watts per square meter of continuous incident solar energy coming into the earth, right? And to have a stable climate, it's no question we need to have 342 watts per square meter of solar energy going out. Otherwise, this guy's cooking, right? But in a sense, so that's in a sense simple natural physics and balance. But what also the Earth has got, it's got an atmosphere around it. Okay, and it's also got a natural greenhouse effect. And what the natural greenhouse, So what a natural greenhouse effect does, it basically, heat comes in, but then it reflects a certain amount of heat back. So it actually retains extra heat in the atmosphere. And that's been critical. For the last 4 billion years on this planet, we've basically maintained a temperature that is 33 degrees centigrade greater than if the Earth was just a simple mineral ball stardust in space. Okay, so this atmosphere, this natural greenhouse effect, has been absolutely fundamental in raising the temperature of that planet 33 degrees above baseline. Okay, it's about sort of 17 degrees now, and it would be, basically minus 16 degrees or something if it wasn't. And in a sense, it's that 30 degrees warming by the natural greenhouse, which is really fundamental because that's kept the oceans liquid. And of course, that's allowed life to evolve and survive in those oceans, right? And of course, the terrestrial biosphere. But what's happened is, of course, we've stuffed that up a bit, and we've basically enhanced that greenhouse effect. So what we've done is we've increased. Okay, we've done two things. We've increased the amount of gases, in the atmosphere. So we've got a thicker blanket. But we've also actually driven up more heat coming from the Earth's surface, which we'll talk about later. And so now, instead of basically 342 watts going back out to space, we end up with a situation where 339 watts per square meter is getting back out to space, but an extra 3 watts per meter squared is being retained in the atmosphere. Okay, so 342 in, balance. Now we've, in a sense, put that extra blanket on, 3 watts. But what you really have to say, this is less than 1% of the incident solar radiation. Okay? And so the question is, what's the natural processes that regulated this system, and what is that we can do to basically bring it back to stability, where again we are basically moving 342 watts per square meter back out to space. Okay, so in a nutshell, hey guys, that's the problem. We've been focused on CO2, but basically it's a simple matter of heat balance on this planet, right? And it's a less than 1% increased escape again of heat from the Earth. So the question is, how do we do it? How does nature do it? And of course, nature does it very, very nicely, very simply. I say simply, but we're going through the details in questions and elaboration, if you like. But it does it through a whole sequence of hydrological processes. I mentioned before that the CO2 component of the greenhouse effect governs 4% of the heat dynamics of the blue planet. 4%. 95% of the heat dynamics of the blue planet is driven by water. Okay? And so really, it's a case of force multipliers. If we've got to cool this sucker 1%, get 1% of heat back out. And here is, in a sense, nature's tool driving 95% of the heat dynamics. It stands to reason even very, very modest, balanced, careful, ecological restoration factors can do that. Okay? I'll go very quickly now because we can elaborate this in detail to question stuff. But in a sense, there's a whole sequence of processes that actually govern the natural heat dynamics of the planet and, of course, govern its natural safe cooling. And we can actually restore those processes through pretty modest factors. And we'll come back because they all revolve around, you'll say the word sponge. Okay? Regenerating the Earth's soil carbon sponge, and they happen naturally. Okay, let's get started. So the thing starts with a sponge. Because if we're talking about hydrological processes, guess what? We need water. Okay? Goes without saying. And the first thing is like, okay, we have roots taking water from the sponge, a tree. Okay, trees are green, not black. Okay, and so here we have green leaves. And of course, we know green leaves transpire, don't they? And so these guys are transpiring water vapor into the air. That's water vapor. But we also know for water to go from a liquid sponge soil into a gas water vapor, we need to, in a sense, have latent heat, or we've got to have enough heat to, in a sense, take it from the liquid phase to the gas phase, right? It's simple physics. You got to, before you can boil off water on a pot on the stove, you've got to put a lot of heat in. And it takes 590 calories of heat per gram of water to take water from liquid to gas. There's a slight variation here depending on what temperature it starts at, but it's all in that 580, 590 category. Okay? And so there's a massive amount of heat needed to transpire water. And of course, where does that heat come from? It has to come from the environment down here, where the tree's growing. Okay? Some of it comes from the solar radiation, onto the leaves of the trees, sure. And that's why trees in high latitudes up in the Arctic are so dark, because they've got to capture as much light and heat as possible to be able to function and transpire. Okay, but basically, by transpiring, you're basically cooling the surface. I live in a city called Canberra, that's Australia's natural capital. It was built 100 years ago by Walter Griffin, Marion Mahoney. Designed, Australians built it, but the point is we've got an urban forest. The whole thing was on a dry, arid, clapped-out sheep paddock, pretty inhospitable site for natural capital as they would. But basically, they built an urban forest, and now it's 7 degrees centigrade cooler on a hot summer's day than the neighbouring sort of concrete jungle suburb, the new suburbs next door, 3 kilometres away, right? And of course, we've got that story all over the world. In Malaysia, they can get up to 17 degrees centigrade difference between rainforest and cleared bare land. And Tom might have sort of data equivalent in the Amazon and what have you, right? So it's really amazing. So the cooling effect, okay, the actual cooling effect of this latent heat fluxes, right? Latent heat fluxes. Okay, they're so powerful that 24% to 25% of the incident solar radiation is naturally taken back into the upper atmosphere by these latent heat fluxes, and that's only with basically the residual forests, the residual transpiring green, which is less than half there was naturally. Okay, so if we can take 24% of that incident heat back up to space through these latent heat fluxes, it's a very simple calculation. It's one factor, and nature's a bit more complicated. There's many factors, but theoretically a 4 to 5% increase in green transpiration by vegetation would cool the planet back to that 3 watts per square meter that we need to cool it. Okay? So very, very simple, powerful factors. There's a bit of a not a problem, it's just nature, it's a bit more sophisticated, because when this water vapor goes up into the air, it also can nucleate, or it can be condensed again as humid hazes. And of course, when it does, basically it releases that 590 calories of energy, but a lot of that up high, because there's less gas above, dissipates out to space. But these humid hazes are actually a bit of a problem, because they absorb incident solar radiation while they're in the liquid form, and then because they're absorbing that incident solar radiation, they actually go into water vapor. Okay, so they again reabsorb 590 calories and go into water vapor. And of course, this is the water vapor greenhouse gas effect. And in a sense, this is 80% of the greenhouse gas effect compared to CO2, which has got about 11%. Okay, this is the greenhouse gas component effect, rather than before when I said 4%, which was the percentage of the global heat dynamics. But all I'm just saying that water vapor is a dominant greenhouse gas, but these humid hazes, in a sense, because they're absorbing incident solar radiation, then make this water vapor. And so, because this is a greenhouse gas, what's also happened, or what also is important, that the level of humid hazes and the persistence of humid hazes in the air is a very, very important factor, in this case, in warming the planet. So, in a sense, here's a process that's cooled it. Here's another, in a sense, sequential process that's, in a sense, warming it. I mean, nature works through fairly sophisticated cooling, warming balances, right? So it's not just one thing switch on, off. There's a whole dynamic. And all we're saying is that as the persistence and the level of humid hazes increases, we're getting a lot of warming. And in fact, a lot of the greenhouse warming that we're getting is because of the extra water in the air. We'll come into how to remove that in a minute. But in a sense, it's that extra water in the air that's a big part of our problem. And the question is, why is there more water in the air? Because we're putting vast quantities of these haze aerosol micronuclei into the air. Okay? So nature put these up. I mean, dimethyl sulfide from algal, isoprenes from forests, terpenes, pinene from forests. You know, these are all natural aerosols that actually form these hazes. But we have massively increased those, because by creating 5 billion hectares of man-made desert and wasteland, we're putting about 4 billion tons of clay dust into the air every year. We're burning the fossil fuels, so that's putting vast quantities of carbon particulates into the air. We're putting a lot of pollutant polyaromatic hydrocarbons into the air. So we have massively increased these nuclei, and of course they're then forming these persistent humid hazes that are actually driving the higher humidity in the air. And that's going from, you know, haze droplets to water vapor droplets. There's vast parts of the planet now, from Cairo through to Beijing, that are basically covered by a toxic brown humid haze. In some parts, in summer now, you're getting sort of, 45, 50 degrees centigrade temperatures, 95% plus relative humidities, way beyond the threshold for humans and mammals to survive, because we need to perspire to keep cool, but you can't perspire and keep cool in those temperatures. So this is becoming a major health effect. So, I mean, it's more complicated than just cooling. There's a whole lot of processes. But the next step in this actual ecology is actually coming to the rescue, because we want the good news here. We don't want to just have bad news. And so the question is, how do we take these humid hazes out of the air? Okay, there's our humid hazes with their nuclei, and as we say, we've basically vastly increased that, because we can measure that with a thing called global dimming. Okay, because basically less solar energy is reaching the ground surface because it's being absorbed by these increased haze levels, right? And in some parts, this is really quite significant. It's up to 20% less incident solar radiation reaching the surface. But we didn't want to talk about that. We wanted to talk about, like, how does nature remove these warming, humid hazes out of the air? And of course, it does that very, 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 very simply. It just basically turns them into these guys called clouds. Okay? Into high albedo dense clouds. And of course, high albedo dense clouds are absolutely effective at reflecting incident solar radiation back out to space. Okay? Half the planet at any one time is covered by clouds, dense high albedo clouds, and they reflect up to 120 on average watts per square meter back out to space. So roughly a third of the incident solar radiation is naturally being reflected. It doesn't even get to the surface. And you know that when a cloud comes over, dense clouds, guess what? You put a jumper on it because it's got cooler, right? Very simple. It happens within minutes. Okay, so up to 120 watts, this is the average. Obviously, it goes much higher, depending on where you are and stuff. And so again, they're very simple. If we have to sort of cool this planet by 3 watts per square meter, okay, we have to rebalance the temperature. Yeah, look, a 2% increase in clouds, in a sense, is that 3 watts per meter squared. Okay, so again, it's more complicated, but here is a single factor process simply increasing the cloudiness or the formation of these hazes, these warming hazes into cooling clouds, can actually sort of very rapidly, significantly cool the planet. So the question is, well, how does nature do this? And of course it does this by this very special thing, which are called hygroscopic precipitation nuclei. Now these are much bigger. These are about 1 micron in size, whereas the other ones were much, much smaller. But basically they're hygroscopic, which means they suck, right? They're just really very, very high osmotic or suction potential. And they're basically coalescing about 1 million of these haze microdroplets to make a cloud droplet, and in that way bringing these warming hazes into cooling clouds. There are 3 forms of hygroscopic precipitation nuclei that we know of in nature, right? And the first, of course, are ice crystals, and you know that when you're drinking scotch or something, and then water forms on the outside of glass because it's hygroscopically precipitating that water. And so in high latitudes, high altitudes, cold fronts, these ice crystals are very important in forming these clouds because of this coalescent effect. Over the ocean, we've got the same thing with salts, sodium chloride, because again, that on the beach you try to have some fish and chips and the salt won't shake because it's hygroscopic, and again, it's doing the same thing, right? It's simple physics, isn't it? It's really no problem. But the most important and the most interesting, and that drives about 50% of the cloud formation and rainfall in tropical inland area, in fact, bacteria. These are highly hygroscopic bacteria, some of the highest hygroscopicity, osmotically, that we know of in nature. And these are bacteria formed in the stomatal cavity of forest trees, certain forest trees, that transfer up with a latent heat flux transpiration, and of course basically nucleating these things into clouds. We'll come back to the next, or we can put it on this slide actually, the next thing. But basically, again, driving this nucleation of clouds, this cooling process. And of course, as you can logically expect, this hygroscopicity keeps on sucking, bringing them together, and okay, they'll produce these guys, right? Rain. Okay, because basically if you take about, what varies depending on the size, 100 to 1,000 of those cloud droplets and make them, then this raindrop is big and heavy enough to fall out under gravity. Okay, so, we've got lots of data on this, some 10 to the 32 bacterial cells are being released by these forests. That's 10 to the power 32, so it's a big number, but plus or minus a few orders of magnitude, of course. But the point is, over half the rainfall in tropical, warmer inland region, from our understanding on isotope measurement data, is actually driven by these hygroscopic bacteria from forest. So again, here's nature, and this is really the point. We'll go on a bit further, but the real critical point here is nature evolved, in a sense, a balance of two processes, right? It's evolved a balance of the haze micronuclei aerosols, dimethyl sulfide, to, in a sense, create the warming hazes that were a key part of the greenhouse effect. Remember, we had it up here. We won't go back, but it's basically creating the water vapor that was part of the greenhouse effect. So in a sense, nature, through the production of these aerosols, creating hazes, water vapor, warming the planet 33 degrees, but at the same time, through the production of these microbial precipitation nuclei, basically creating the opposite cooling effect. So here we are, a feedback balance between haze generation, cloud generation, rainfall generation, and cooling. So warming and cooling, totally regulated by these microbial precipitation, either haze or precipitation nuclei. Okay, so we come into this really amazing question that, basically how much is rain and the hydrology of the atmosphere actually driven by a biological process, a biological balance in this hydrology. To what extent is rain in these forests, above these forests, like the Amazon, actually a symbiotic process where the trees are actually generating these precipitation nuclei that are creating the rain. So we've always known that trees need rain. Now we're asking the question, does rain need trees? Okay, whole new paradigm. Hey, opens it all up. Actually, very important to understand that even over the world's deserts, there's rivers of water flowing across them continually. Up to 50,000 parts per million of that desert air, whether it's Nevada or Death Valley, can be water vapor. 5% by weight, water flowing across these deserts. 50 centimeters of water. Up to, right? Not always, but up to 50 centimeters. So nature, in a sense, again, has harvested this water, whether it's cacti or special foliage on sequoias, for example, right? They get 70% of their moisture from harvesting this humid airflow. Why can't we? Because basically we've got 5 billion hectares of man-made desert and wasteland. We need water. We need sponge, we need cooling. Okay, story goes on, but I'll go a bit more quicker, but how are we going for time actually, Alan? 10 to go. Okay, well look, just very quickly. I'll go more quickly, we can come into it. Once we have rain, we do another thing. We reopen the nighttime radiation window. That sounds sweet, and it is. Basically, 60% of the warming that we've recorded to date under climate change is actually due to increased nighttime minimum temperature. Why? Because the re-radiation from the Earth can't get back out to space. Okay? But of course, once we have rain through these precipitation nuclei, we have clear skies. In the tropics, that's where Somerset morn, the moonlight and stars, like it's early evening, and all that massive re-radiation of heat going up into the air. And again, by removing those humid hazes, by removing that water vapor, we're reopening those nighttime radiation windows. And again, they can be varying, depending where you are, 30 to 40 watts per square meter of cooling effect. So very, very powerful in the tropics. Another thing I wanted to mention, which is really actually much, much more fundamental. If we have a soil surface and we have this soil covered with vegetation, right? And we have this soil which is moist because it's got a sponge. Okay, then what we have is basically, we've got solar energy coming onto that soil surface, reflecting in an albedo effect, and that can be sort of from 20 to 70%, depending how white and reflective the surfaces are. But the point is that because of the moisture, and of course these moistures is creating latent heat fluxes, as we said before, this soil very rarely gets above 20 degrees centigrade, right? And it's quite consistent even in tropical regions, right? Because basically we've got cooling processes, both reflections and latent heat fluxes. Conversely, where we leave that soil bare, dry, exposed, and we've got the same incident solar radiation hitting it, that heat will all just absorb into the soil. And these soils will often go, and we can actually confirm it's higher than that, 60 degrees centigrade. Okay? So we can really sort of cook those soils. I mean, basically they're really inert because they're bare dirt. They've really got to mineral, desert. And there's a very, very, very powerful thing that happens. And it's a simple rule of physics. We can't escape it. It's a bit like gravity. It's called the Stefan-Boltzmann equation, right? And the Stefan-Boltzmann equation says the amount of re-radiation from the Earth is proportional to a constant times the fourth power of the temperature in degrees Kelvin. Okay? Physics 101, you guys got it. But the real guts of the thing is this guy. You see, because basically Kelvin is minus 270, so you've got to calibrate with the temperature, but basically it's temperature times temperature times temperature times temperature. Okay? So the amount of energy being re-radiated from the Earth's surface is fundamentally higher here, right? Okay? Because basically of this fourth power function in that black body radiator, right? Can't escape it. And see, that's in a sense so profound. Because if you guys realize what the greenhouse effect, and you've never been told this, so hey, you're the first to know. The greenhouse effect is driven by two factors. And this is hard science, nobody would argue with you. The first one is the amount of re-radiation, the amount of heat going up, right? And the second factor is the amount of basically re-radiation absorbed by gases, greenhouse gases. And the key one is, of course, water vapor, which does 80%, as we said before, CO2, which does 11%, and then, your methane and nitrous oxide, etc., right? And they do about 8%. And then there's CFCs and others, right? So that's what the greenhouse effect is all about, guys. Okay? So it's amount of re-radiation and then the amount of absorption. And so far, we've been talking here to say, look, we can reduce that water vapor greenhouse because we can turn it to clouds. Conventional science has really been locked into this game, hasn't it? Can I basically play around reducing that 11%? But we've already agreed this will take a century, 100 years plus, right? Okay, because of the ocean re-equilibration. But if you really want to get smart, if you really want to cool the planet, you just turn the stove from high to simmer. right? You basically reduce this. And how do you reduce that? You already know how to reduce it because you've got physics, you've got stimulus. Oh, come on, guys. Paper. Okay, you see, we've got an equation that tells you how to do that. Because if you keep your soil moist and cool, okay, you can reduce that re-radiation 80-90%. Okay, so you can turn down the greenhouse effect. You can do it in days. It's as simple as not mowing your lawn. But sponge. Okay, that's the key thing, the sponge. Okay, so you've got to rebuild that soil carbon sponge to one, have the moisture, to have the green, to have the transpiration. So it all comes back to the sponge, rebuilding the Earth's soil carbon sponge. Okay, so look, I think I'm going to wind up there, really. We can go, there's more processes and more exciting stuff, but I think the guts of it, we can understand that we can naturally, safely cool this planet hydrologically, safely, naturally. Oh, I've said that, haven't I? So basically, we can cool this thing, but it's all about rebuilding this hydrological cycle. Now, rebuilding the sponge, aerosols for hazes, precipitation nuclei, and they all come back from what we add here, you see, because as we basically look at this 250 billion tons of carbon dynamics, see, this is when we don't burn those forests, we don't putting up those carbon particulates, we're not putting up those aerosols. When we extend the longevity of green, we're again sort of basically putting up more precipitation nuclei. So really this is revitalizing, regenerating that biosphere that we all evolved in, we all depend on fundamentally. Innovative farmers, the guys that we involve with, yeah, they're doing 10 tons of carbon per hectare per annum, sustainably, productively back into their land. Okay, so there's 20 billion tons of carbon drawdown. It's 2 billion hectares, of the 14 billion hectares of the planet at that rate. But even if we're doing a fraction of that, in the bottom line, we can do it all ourselves. We can have power ourselves, whether it's a balcony or courtyard or urban agriculture or forestry or grazing, we can regenerate green and we can safely hydrologically cool the planet. Thank you very much.
First, the 8 billion tons of fossil fuels that's in that curve, what's the other 122?
Okay, no, very good question. I mean, basically, as we said, forest fires, that's about another 10, cement manufacture, but it's also you and me, right? Because, and it's nothing bad about it, we've got to respire, right? We basically are using sugars all the time, and as we burn those sugars in our body, we breathe out CO2. So I breathe out, you breathe out about 1,000 parts per million CO2, right? No problems. The plants need that. So it's a balance always, right? But basically, all right, of that, some 70, 80 billion tons is respiration, is natural biological, breathing.
Okay, this is my second question. I watched your YouTube presentation of this as well. So I'm, getting more and more foggily, a little bit understanding of your situation, your description. However, they say we have like 10 years to solve this problem. What I'd like to hear you say is, here's what I would like to see happen. This is the plan. Because where I live, when I said I'm going to this talk and he's so interesting and, carbon dioxide is really only part of the problem, they said, you know what, that kind of talk just keeps us from the real work, which is carbon dioxide. And what I would like to say is, no, here is the plan.
Okay.
Here is the way forward.
Right. Thank you. And look, I 2 points. First of all, no one's saying we mustn't reduce carbon dioxide or negate that effort, right? But we're just lifting the context of it into 250 billion tons of dynamics, not just the 8 billion tons in fossil fuel, right? So we're just extending the potential. But no, the bottom line is we're absolutely committed in Regenerate Earth to 20 billion tons of carbon draw. I mean, that 20 billion target, very, very tangible, strategic, committed actions. But the real message tonight was, yes, that has to go into the sponge. It's only if we can put it into the soil to rebuild the hydrology, to rebuild the cooling and that hydrological thing, that we've got a chance to avoid those dangerous hydrological extremes. As far as the 20 billion tons, yes, we can partition it, got detailed papers. Yes, so much from forest fires, so much from cement, so much from reforesting, the 3.5 billion, regrowing that 3.5 billion or increasing growth, so much from shelter woods extension into arid land, so much from ecological grazing. So there's about 8 key components, and they all add up to over 20 billion tons. But basically we're saying conservatively, practically, we're doing that. And yes, there are strategies in play to actually do each of those components. So, for example, we've got a major fire versus fungi initiative, and that's really taking off basically in Australia, where I live, but also it's being picked up in places like Spain, Portugal, other places. Quite frankly, New England very, very quickly you've had this story now in New Hampshire, where you are going to sort of basically have a bioenergy burning of those forests. And hey, what consequences does that have? So yes, there's an action agenda. Sure, it's not out necessarily fully documented in public, because this is basically working with those innovative groups, doing all those initiatives. But are there other comments, people?
Yeah, I just, I lived in Texas for a lot of my life, and Texas started dehydrating about the time the beaver disappeared. And I would like to say, I like what he did here with this idea of the difference between land that is covered with vegetation and the land that is exposed. 3/4 of Texas now is exposed to sunlight, and there's no way to do anything right. And it's kind of like, when the rain does come down, we have to hold the rain in place and not let it get away and let the vegetation come back. So I think this is a huge opportunity, because he's bringing the water cycle into it more. But if we have bare ground dominating and this is California too. If 10% of the Central Valley was beaver managed wetlands, Central California wouldn't have a problem.
Absolutely.
So that's.
Yeah, some of the things that we were proposing when we were speaking with communities, Walter said, mowing your lawn less or letting it grow a little taller. So in terms of that, increasing the transpiration, increasing any kind of acreage, leaf area, height, or longevity of green is going to be cooling through those latent heat fluxes, and that's local cooling you can benefit from right away. Same thing, any area that was bare, whether it's bare pavement or bare soil, that you have now green plants growing on, is not only going to cool through the latent heat fluxes, but also dramatic cooling because of that lessened re-radiation. So those are 2 really low-hanging fruits, both in urban areas and in agricultural areas. For example, the Central Valley in California, one of the things we're proposing is that if all of those farms simply use cover crops, a 25% increase in green transpiring growth on agricultural lands alone, in theory, in the sense of just that part of the whole equation, would reduce the warming that we've already seen. So is that doable, to have 25% less bare ground? If you look at Google Earth at agricultural land and look at how much of it is brown on the solstice, the summer solstice, you'll see that yes, we could do a lot more green. So, and that's not a big ask of farmers. So there are big cultural, economic, policy stumbling blocks in the way sometimes, but a lot of those are being addressed through soil health bills.
Just a
very quick factual thing. To increase the sponge effect, and I'd never heard it talked about as a sponge. So I understand we have to increase the ground cover, and you also mentioned increasing fungi, and I wonder if you could just say in very specific terms what exactly needs to be done on a vast scale to increase the sponge effect.
Tom,
Thank you.
That and I'll go into it. Look, very simply, the sponge, and we talked about these cathedrals of voids in the soil. Hey, we got a blank page. Way right. Okay, so look, it's actually quite exquisite and beautiful. Okay, if you have a rock, if it's a sandstone, it's got a bulk density of about 2.6 grams per C. If it's an igneous rock, 3.5. Right. That means it's all mineral particles, no air, no voids. But if you've got a healthy soil, we're coming to sponge, it's got 1.1 grams per cc, right, in terms of density, which is telling you that 66% of it is basically voids, nothing. So you build healthy soils by adding nothing. Easy, yes, easy. Doesn't cost a thing. Okay, but the healthy soil is like this. Okay, there's mineral particles, okay, and basically these are sort of glued together and held apart by these organic matter matrices. Okay, and this only has to be 3%. But because you've got those, you can actually end up with massive voids, capillary water voids, right? And so it's here where water infiltrates. It's here where roots proliferate down. Instead of being stuck with 20 centimeters soil or root growth at the surface or less, hey, these are natural soils, your prairie soils going down 5 meters. So the volume of soil resource that you are empowering and creating through the sponge is enormous. So basically the sponge is just adding nothing, right? This is nothing, this is voids. Okay, but it's basically the fungi that really are the things that, in a sense, one, create this organic matter or the carbon from organic matter, but they also glue these soil particles together as, in a sense, builders and build this sort of loose matrix of three-dimensional soil, right? And also what happens, this is really critical in terms of the biofertility of soil. Okay, 90%, up to 90% of the biofertility of soil has got nothing to do with more on agriculture and how much you add to it. It's all got to do with the surface area of exposure, because here's where your calcium, your magnesium, your zinc, all those essential cations and micronutrients are basically on that stardust, on that mineral particles. And now they're exposed, available to roots and fungi for uptake as biofertility. Before, they were unavailable, locked up, inaccessible. Okay, so the sponge very quickly gives you water, it gives you nutrients, it gives you rootability, it gives you microbial ecology. There's 10 times more life, biomass weight, below our feet than there is above it. Okay? And it gives you then the productivity and the resilience. And yeah, this is the sponge.
So in terms of how to build that sponge, if you look up soil health principles online, there are various groups, including my website, that has versions of that. The NRCS, which is a branch of the USDA, the U.S. Department of Agriculture, has really taken this up. They have a whole soil health team that's working with farmers. But the essence of it is that plants, when they're photosynthesizing, they're taking that CO2, taking water, and turning it into themselves. And then the extra sugars that they make, they feed out through their roots to feed the biology of the soil. And part of the biology of the soil is the fungi, the mycorrhizal fungi that have a symbiotic relationship with the plants, go access those nutrients, bring them back to the plants in exchange for sugars. So simply having plants growing long-term in the soil and not disturbing it will feed that underground life. There are things you can do to speed it up. There's, certain inoculants, compost, etc. But, sometimes that's more complex than it needs to be, because you'll see that, if you go anywhere in nature, that if you leave things alone in an environment like the Northeast, things will start growing. We call them weeds, but those weeds are the first responders. They are there because the soil is bare. They're like a scab, like a Band-Aid, like a first responder trying to quickly pump some sugars down into the ground. And you'll see the weeds. The weeds are often the ones that have the biggest leaves that can access the most light, like what's the one that everybody's so upset about around rivers? Yeah, Japanese knotweed. Okay,
yeah.
Beautiful photosynthesizer. Or they have deep taproots that can break down through that compacted soil, like dandelions, burdock, etc. The other things that we say, hey, get these out of here. But why do you have something with big leaves or a deep, strong root growing there? Because the soil isn't a sponge. So, or poison ivy growing at a roadside because it's very sandy and salty and nothing else can grow. So whatever will grow, and it's trying to grow the sponge.
Yeah. Tom?
If you last point here, that if you take, so I like to compare degraded soil with flour. Water runs off, you can blow it away, doesn't hold together, no matrix, and healthy spongy soil with bread. Imagine pouring water onto bread. If you throw that bread in a blender, do you still have that sponge effect? No. So tillage, eliminating or minimizing tillage, rototilling, is a really key piece to long-term building of the sponge.
I just want to add that we're finding out that there's an economic system below the surface. Plants, half the carbon they make or more in healthy systems, they're giving it to fungi. Fungi are taking a lot of that and giving it to microbes that make acetic acid to actually drill into the little minerals and find the phosphorus or whatever. When we add nitrogen fertilizer, like they did in West Texas to grow corn or whatever, or cotton, they turned it to concrete because it became a bacterial soil. It was just, it just killed the fungi networks. Another system is as all the worms and nematodes and whatever in the soil consume all this carbon and redigest it and redigest it and redigest it, they're cooking it again and again and again. And what comes out is something that's very much like, it's very humus-like. It's very high in carbon. It's got a lot of surface area. It's like this biochar that we talk about. That was done naturally. And that'll hold on to all the minerals. It's very electron dense, so minerals are attracted to it. So this whole system is, we're just starting to learn about it. And what we're finding out is our industrial agriculture has killed a lot of it. So that's kind of why we're in a little bit of trouble. So.
And just in terms of things that we can be doing, there are 42 million acres of lawn in this country. Everybody has the potential to get some deep-rooted perennials growing, and that helps to build the soil carbon sponge. Depaving, which would not be a bad thing for us to consider doing on whatever scale we can, but getting rid of the surface that we've put over the soil. You, one of the leaders of that movement, one of the founders of Depave Somerville, is here in the audience. But as soon as you take that concrete away, you don't have to throw any seeds down. The seeds are there and they start to grow. They have just been waiting to be freed. So we do have a great deal that we can do locally.
Yeah, okay. I think to support what Walter says with a historical analogy. Now, sorry, that loud enough? Yeah, with the historical analogy. Now, the thing is that worldwide we've destroyed more than half of the biosphere. Cut down the trees, the carbon's gone, it's oxidized, turned into CO2. Now, the amount of carbon that was in the biosphere was more than the atmosphere originally. It's less now, okay, because we transferred back up. But the amount of carbon that was in soil, there's a lot of controversy about that. Traditionally, people would say there was 3 or 4 times more carbon in the soil than in the atmosphere. That's because people didn't want to dig very deep. there's a lot of hard work to dig a hole, 10 feet deep and measure the carbon. So they'd only go down this far, they'd measure the top 10 centimeters or so. And that was at that 3 or 4 times more carbon was. Now that people dig deeper, of course, there's all this carbon they didn't measure before. And now, the view is that it's 5 or 6 times more carbon in soil than there is in the atmosphere. Some people say that's a flat Earth hypothesis because that's just the surface area, but in fact, the Earth is not flat, it's up and down. So that about doubles the surface area. So maybe it's really 12 times more carbon in soil than the atmosphere. So you don't need to increase it very much to absorb that excess. Now, so we've done a huge jump. We've wiped out half the carbon in the soil in every place we've converted from forest to agriculture or pasture or urbanization. So that's maybe 5 or 11, 10 times more carbon than is in the atmosphere that we've lost from the soil already. Well, a lot of that has wound up, going from the atmosphere into the ocean. But we've really disturbed the system a great deal. Yeah. Now, sorry? Yes, okay, sorry. So if we regenerate the carbon cycle, well, how would it affect the climate? 35 years ago, I was working in the Amazon in Brazil, and I set up the first lab in Brazil to measure greenhouse gases at high precision. I was measuring the effects of Amazon deforestation on the chemistry of the atmosphere. And we were measuring greenhouse gas emissions in undisturbed Amazonian jungle in places been clear-cut that were 100 meters away. Same forest, same climate right next to each other. They went in with the chainsaws, they cut everything down. The rains came before they could burn it down, so they walked away and abandoned it. Yes. Virgin Amazon jungle turned into a pile of rubble. And they just abandoned it. They didn't burn it, they couldn't bring cattle in, they just walked away from it. Now, I was measuring temperature in the air and in the soil through day-night cycles, night and day. And when we were in the jungle, in the jungle, the temperature difference was, less 1.5 degrees centigrade from day to night. It was always cool and pleasant in the jungle. There was always green vegetation on the ground and so forth. In the clear cut, the temperature fluctuation from day to night was something like about 18 degrees centigrade instead of 1.5 or 2. It was more than 10 times greater. It was much hotter. It was unbearably hot in the same area. That area, the soil had baked into concrete-like hardness. All the vegetation was brown and dying. This was, short, dry season, but there was severe drought going on in the clear-cut areas. And the temperature was unbearable. You walked into the forest, it was cool. The difference is the evapotranspiration, because most of the solar energy, as Walter said, that goes on the land, goes into evaporating water. And about 90% of that water that's evaporated isn't evaporated, it's transpired through plants. It's not physical evaporation, like what happens in the ocean. That's water that the plants are sucking out of the ground, passing through the roots and releasing. And every molecule of water they release, they're sucking heat out of the ground, out of the leaves, and releasing that into the atmosphere, because that's the heat to vaporize the water. When that water condenses and falls as rain, that heat gets released. Then that drives the circulation of the atmosphere. So the forests are driving about 90% of the water vapor transport from the land, from the ground into the atmosphere. And they're responsible for about 90% of the heat transfer. Yeah, that's really important. So now, what has happened worldwide is that every place we cut down the forest, it became unbearably hot. And you have to have been there at the time of deforestation, at that time, to have experienced it, because the next generation never remembered. And every place in the world where people encountered deforestation, every place they tell the same story. That the land was cool and green and the rivers flowed year-round, and we cut down the forest and it became unbearably hot. Unbearably hot. The springs and the streams dried up and they ran only in the rainy season. The land was baked brown almost all the year. And people tell that story every place. And, Plato and Aristotle tell that story about the deforestation of Greece. Thousands of years ago.
Absolutely.
So it's the human experience of every single culture that they made their land hotter. But you had to have been there at the time to experience that. But now, everyone who plants a garden in an area that's barren and turns it back to green into life with those plants sucking heat out of the ground, it's just pleasant to be in those It's just so much cooler in the surrounding area. Everyone can see and experience that.
I would like to understand more about flood and the consequences to the soil. How, for example, flood creates drought.
Okay, well, look, it just goes automatically, you see, because if you have a storm and just say there's 1 inch of rain, and the question is, yes, if it's flooded off, you don't have that inch of rain in the soil, and so your soil has got no water to keep growing. So by definition, you've got a drought. So a drought is an automatic reverse of the flood, right? You have a flood, you've lost the water. Because you've lost the water, you've got a drought. And it's a paradox because we always see them report in the newspaper, oh, we've got floods, disaster, disaster. Hey, we've got droughts, disaster, disaster. They're one thing, right? And really what nature does, in a sense, it conserves that water in the soil, infiltrates it through the sponge, retains it in the in-soil reservoirs and deeper aquifers, and that extends a longevity of green growth, which in a sense avoids a drought. So as we had in this graph here behind Tom, you see that red line, hang on, here we are. This red line is in a sense extending, and as I said, we're continuing green growth sometimes for, 10, 20 times longer than the amount of time in a flood situation, right? So it's that simple. It's inescapable. You've lost the water. You've got a drought.
Let me add to that because it's organic carbon, the organic material that holds almost all the water in the soil. The more carbon you have, the more you retain water in the soil, the more you extend your growing season. I'm going to tell just a story from his country because I was in Australia last year and I was in Queensland on the hottest day they'd ever had in their history. And it had the worst drought they'd ever had in Queensland. All the sugar farms were baked brown, no vegetation, completely, the soil had crumbled. And in that area, I went to visit an organic fruit farmer who plows all his carbon back into the soil. His neighbors had 1% carbon in their soil. The soil was dry, crumbled it fell apart. His soil had 6% carbon. The trees were green, it was cool and pleasant to be in his yard. Now, when the rain comes to the neighbor's yard, what happens is all that soil washes away. So the rivers are filled with mud. And I worked with the Aboriginals. I filmed with the Aboriginals on the coral reefs downstream from those rivers. They lived off fishing those reefs. They're now piles of mud. The reefs have been completely killed by the mud coming off bad agricultural land management. On the other hand, my friend who's the organic farmer, Andre Liu, who I think you know well, you look at the rivers flowing off his land and they're not full of mud. They're clean and clear because the organic matter is holding in, retaining it, and releasing that water very slowly. You can see a huge difference just from one garden to another.
Good.
Anyone can do it.
Absolutely. Yep. Didi?
If you go back to the bread and flour analogy, I know some of you have seen me do this hundreds of times. If you haven't seen it, you can look at rehydratecalifornia.org, and there's a video there of a talk that Walter and I gave at Piscinas Ranch in California. And essentially, this is a fun thing to do at a dinner party. You have a plate with a pile of flour and a plate with 3 slices of crappy gas station bread, and poke some holes in a cup. Talk about the flour is just the mineral portion of soil. There's no organic matter, there's no carbon, there's no biology, no life sticking those mineral particles together. You can blow on the flour, it'll blow across the room. Poke some holes in a Dixie cup and rain on it, and the water's gonna run off. You're gonna have erosion, you're gonna have muddy streams around the edge of the plate, a flood around the center, around the edge, and a drought in the center of the plate, right? If you stick a little piece of grass in there, the roots aren't in anything. There's no water there. Then what do you do to take flour and turn it to bread? You add biology. In a landscape, that's the plants feeding the microbes, feeding the fungi, and all of that whole soil food web up to earthworms, up to all the other life that lives in soils that the roots are going through, making passageways. These little particles are getting stuck together. There's those voids and cathedrals in the soil. If you rain on that bread, where's the rain going? It's going down through those pores all the way down to the bottom of the plate. And if you have the streams are still around the edge, they're getting refilled year round from the bottom, from springs coming up out of the ground. So that's why you don't have a drought there. It's because of those voids in the soil, because the water can sink down and stay down and come sideways into the rivers and streams and lakes.
Great. Yeah.
One tiny addition to that, in terms of your flooding, if you've got an area that's flooded many times and you've got big gullies, well, that means that the water table is going to drop to the lowest point of that gully every time, because that's a way to get out. So what you want to do is stop, the gully. That's what the beaver roll was or whatever. But if you stop that water in the gully and let it build up and raise that water table a little bit, and then you can start rebuilding the sponge, because the water will stay in your area for longer. The beaver plan is if you get fresh water, the beaver plan is to keep it on the land as long as possible until it turns into vegetation. The human plan seems to be to get rid of it as fast as possible. And this isn't working very well for us. So,
can I ask another question?
Yeah.
Or
Yeah,
I have
okay.
Walter, I would nominate you and I would vote for you right now as czar of the world. Because I actually
Hey, I'm an innocent bystander from down under.
I actually think that if you were the czar, then I would feel very hopeful about what you said tonight. It turns out that I missed physics. I transferred schools and never took physics. So I feel very privileged to have sat through this tonight. And it's been tough for me to follow with that lack of physics. But, I've spent an hour listening to you. Very few people in this country are going to spend an hour, whether it's physics or not physics, listening to you. So I think if you were the czar and you could do this on your own, and you could make the earth do what you've just said it can do very simply, I'd have great faith that this is a solution. The problem is, like in the end of Lion King, we find out that humans are the most violent and most feared species. And in fact, everything we've talked about tonight, the Amazon doesn't light itself on fire. People light it on fire. The forests in Southeast Asia don't get lit just on their own. Very unlikely. Some lightning strikes, but mostly it's human beings. So Dee Dee touched on this, where she kind of just went into the cultural, political, economic, and we can go on and on, in terms of what are the factors that lie against this. And the last thing I'll add to it is when I hear that Aristotle was observing and saying the same things that we're feeling now, it does not give me a lot of hope that there's suddenly going to be a change in human nature and all these human factors that deal with nature without a czar who just says this is what you're going to do and people do it. So I'd like to have an answer to the first question here, which is, what do we say to people when we say, how is this change going to happen?
I'm going to interrupt here. Because Bio4Climate, we wrestle with this. We've been wrestling with it for 6 years, which is not a very long time in the scheme of things, but we're really pretty wrestled up. And I've gotten to a point where I don't blame humans anymore. I think we're all biological creatures and we react according to our biology, and we can make some changes. And I think we are making some changes. Apropos of people hearing Walter, we have something like 220 videos from all of our conferences on YouTube. And Walter's talk from last year at Harvard is very near the top of the list, even though he was a latecomer to that list in that respect. So people are listening to him. We've had over 150,000 views of our videos, and we are reaching people, and people are being ready to be reached, and because what's doing the talking now is nature.
Yeah.
And that changes everything.
Yeah. And Adam, may I just quickly add, look, it's not me. This is all about empowering you. You know, basically, this is very simple, basic, empowering everybody, every child on the planet to say, yes, they can build a sponge simply through compost, weeds, and those processes. And you're right, it was Aristotle and others. Your president said a nation that destroys its soil destroys itself. That was Franklin Roosevelt, Dust Bowl. So, you know, we've had those warnings, but also you're absolutely right. Look, there's no problems on Earth. Nature will fix it. You know, nature's fixed this, as in petagenesis, every time there's been a meteorite or big volcanic. The only question is, will we actually wake up and help her do it? Or will she basically do it after Homo hubris is gone?
So the only thing I disagree with, Walter, is that you're not going to do it for us. And we have a whole bunch of lawns that are waiting for you tomorrow before your plane takes off that you will responge for us.
No. Okay.
Worried about politics, the soil health movement in the United States is actually bringing together very conservative people and very liberal people towards a single aim. And it's a beautiful thing to go to some of these conferences.
Yeah, blessed unrest. And that's a terrific point. This is not political. You can talk to people all across the political spectrum and have lunch and dinner and sing songs. And it doesn't matter who you voted for or who you will vote for, because Earth abides forever.
Yeah.
So,
It's a sponge, right? A sponge.
so thank you all for coming tonight.